Hello, everybody. Hope you can hear me. My name is Matt Hipsey from University of Western Australia, School of Agriculture and Environment. And it's my pleasure to kick off our New Look Environment Seminar Series on our new online version. It's great to see so many people have already logged in. We've already got over 40 people ready to go, which is fantastic. We're delivering this from a lecture theatre, our Simmons Lecture Theatre usual location, with no people in it. So it's great to know that everyone's out there listening. It's my pleasure to introduce today our speaker, Don McFarlane. Don is going to kick off the New Look online series for us. It's really great to have Don be able to introduce this seminar. Don's got a long history in water science in Western Australia. Did his PhD in hydrogeology at UWA. He worked in the Department of Agriculture for many years. He worked as a director in the Department of Water. He subsequently worked leading the CSIRO flagship in Water for a Healthy Country. And recently he's been working as an adjunct professor here at UWA, sharing his experience with the next generation of hydrologists. So it's wonderful to have Don here. He's got extensive experience and he's unique in Western Australia, being able to provide such a holistic view of water resources right across that southwest corner, which of course is adapting to many challenges over the last couple of decades. So just without further ado, I'm going to pass you to Don, but a couple of little housekeeping things to mention. I think many of you are getting used to reality on Zoom, but for those of you not quite used to using Zoom, please just make sure you're on mute. If you've got questions, that's fantastic. We've got a chat function you can type into as you are going, and we'll monitor those and moderate those questions at the end. Also, you'll be able to ask your question in person at the end as well if you would prefer. So without further ado, I will hand you over to Don.
Thanks for that, Matt. So the talk today is going to be looking at both surface water and groundwater resources in the southwest of Western Australia, and looking at their response to past climate change. So this is not one of those future ones based on modelling or anything. This is actually looking at the results of past climate change on the surface water and groundwater resources, particularly of the southwest. So it's quite a wide scope. It's actually looking across a large geographic area, and people don't realise that the southwest of Western Australia, the area of it is equivalent to New Zealand and also to Victoria. It's a very large area. And also we'll be looking back up, in some cases, some of the climate data goes back to about 1910 up to the present day. So geographically, it's a very broad look at what's happened. And I wouldn't even attempt to do that by myself, but I've got a number of co-authors that have also got a lot of experience in working in the southwest. Richard George from the Department of Primary Industries and Regional Development down in Bunbury. He's got a long, extensive history in dryland salinity work particularly. John Ruprecht, who's now at the Murdoch University, has been a surface water hydrologist for a number of years. Steve Charles, who's done a lot of work on climate in southwest Western Australia, and Jeff Hodgins, who's a data analyst and the mapping guy also at CSIRO. So really a number of these the slides that I'll be showing today have actually come from those sources. Now this is as I say, quite a wide scoped project, so I'll actually have some summary slides as we go through. So if it's a bit complex at some stage, hang in there because there will be some summaries coming up. To go down. It's not working. Oh, here we go. I just want to say too that we've actually published a paper on this. This talk is based on a paper we've published in the Journal of the Royal Society. It's free, available online. So if you're interested at all in what I'm going to present in the next little while, there's a lot more detail in that paper with the same co-authors. There's a URL there. You wouldn't need to write that down because this talk and the slides will also be on the web at some stage after the seminar. So the Southwest WA is unique in a number of ways, and so I need to spend a little while going through some of the unique features of it. Now, this is a picture of the Yilgarn River, one of the big inland rivers, which flows out of the Wheatbelt. You can see some granite outcrops in the distance, and this is obviously taken from one of those granite outcrops. It's a very extensive drainage system, very ancient. The rocks are very, very old, but also the landscape's very, very old and leached. And that's a saline river system. There was a lot of primary salinity there, but it's actually got worse as a result of clearing. So just looking at the topography of southwest WA, we'll be looking at 4 hydrologic zones in this talk. There's an inland zone of the Wheatbelt, which has been extensively cleared. It's very flat, it's elevated. When I say elevated, the orange in this elevation map is 300 metres. The yellow is about 200 metres and the green about 100 metres above sea level. So this is still very low lying. It's elevated, but it's not very, very high elevation. So you can see these broad valley systems, so that this is the Yilgarn and the Lockhart coming together here. That's that photograph I showed you at the beginning. It then enters an area of rejuvenated drainage, where the drainages are much more incised into the landscape. And we call that the zone of rejuvenated drainage. And the eastern part of that has actually been extensively cleared, but the western part of that is actually the Darling Range, which is still under Jarrah Forest. Then in the west, we've also got the Perth Basin, which is a sedimentary basin. It's largely low-lying, though there are a couple of elevated areas, the Blackwood and the Dandaragan Plateaus. And particularly, draw attention to this blue area, which is the Swan Coastal Plain. Some people confuse the Swan Coastal Plain with the Perth Basin. It's actually a subset of the Perth Basin as the Swan Coastal Plain. Very low-lying, very sandy, and it's got extensive water resources for which we'll be talking about the impact of climate change on them later on. So they're the 4 zones, and I'll be going through them from west to east. And I'll talk a little bit about the groundwater first, and then talk about the surface water result afterwards. So there's a bit of a system to this talk. Vegetation cover I've mentioned, they're the 4 zones again, but you can see that the main areas that haven't been cleared of the native vegetation is the Darling Range, and also the Blackwood Plateau part of the Perth Basin. But mostly the rest of this area has been cleared for dryland agriculture. Now, this is important because perennial vegetation has a massive impact on the hydrology and how it's actually responded to climate change. Another feature of southwest Western Australia is it's got an enormously higher rainfall than would be expected for a continent in the southern hemisphere on a westerly aspect, because the oceans currents from the south to the north, so they're very cold. And most parts, and I'll show you a table in a few minutes, most parts in South America and Southern Africa have very, very low rainfalls. But the southwest WA has enormously high rainfall because of the Lewin current. And what we've got here is 2 images showing the Lewin current, one under El Nino conditions, and you can see this warm water, the yellows and reds going a bit further south, and the dark blues being pushed back. Under La Nina conditions, it's even stronger. This is a very much stronger current, and actually it affects sea surface temperatures. And because sea surface temperatures are higher, you tend to get more rainfall. If you don't believe me, look at this table we've produced here. So this is Western Australia, Chile in South America, and Western Africa. And these are positions at the same latitudes. So we've got Geraldton versus Copiapó in Chile. So Geraldton gets 460 millimetres per annum, Copiapó gets 12. So this is part of the Atacama Desert. And you can see that the equivalent place in West Africa is only getting 46 millimetres. So if it wasn't for that Lewin current, we would be in a very dry situation. As you go further south, the difference is reduced. But even at Bunbury, you can see that we're getting almost twice as much rainfall as we'd expect for that latitude. Now, one of the interesting things about this is that some climatologists are saying that the El Nino events are likely to become more intense and prolonged in future. If that's the case, then that Lewin current won't be as strong as it is at the moment. So now we're looking at how the climate has changed. And I'll be particularly in this analysis looking at what happened since 1975, and as a subset of that, what's happened since about 2000. So that there's before 75, between 75 and 2000, and then after 2000 are the chunks of time we're looking at. Now, this is two isohyet maps. So if you look up here in the top right-hand corner, so you can see what the isohyets are for the southwest of WA between 1910 and 1975. You can see large areas down here where we're getting more than 1,000 millimetres of rainfall, sometimes 1,400 millimetres, and up here perhaps only 300 millimetres. So it's a very large rainfall gradient across the southwest. When you plot the 76 to 2017, you can see that some of these areas have got much drier. And this main map we've got here is a difference map. So you can see that for particularly the western third of the area, since 1975, we've had a 10 to 20% reduction in rainfall. This is an annual rainfall thing, so this is looking at the percentage change. So that's what's happened before and after 75. If you look at the next map, we're looking now at what's happened before 75 versus what's happened since 2000. And you can immediately see that the area that's had more than 10% reduction has actually expanded a little bit more. But specifically, we've got now some areas where we're getting 20 to 30% reductions in rainfall. So the drying trend, if you like, has got more extreme in those last 17 or 18 years. Now these last two maps have been annual rainfall. I now want to look at what's happened in the growing season, which is the wettest 6 months of the year. So about 80% of the rainfall in the southwest falls in that the wettest 6 months of the year. And this is very, very important from obviously from an agricultural point of view, but also from a runoff and recharge point of view. So we're looking at May to October rainfall and the percentage change before and after 1975. And now you can see that the area that's had a 10 to 20% reduction is actually more than half of the southwest. And there's even some of this area that's had more than 20 to 30%. So this is, what it's saying is that the winter rainfall, which we call the wettest 6 months of winter rainfall has dramatically dropped off compared to the annual rainfall. And when you look at what happened before 75 and after 2000 for that 6 month period, now you see a very substantial impact of a drying climate, particularly in the northern regions. So we're getting some areas here of more than 30% reduction in winter rainfall. And also you can see that the drying is also starting to affect the southeastern part of the region as well. So Esperance is showing up as having a reduction in winter rainfall, particularly since 2000. Now this is important because we will actually see the impact of this drying, particularly the winter drying, on salinity, but also flooding and runoff into the hills dams. Just to get an idea also of what proportion of the rainfall has been occurring in winter and summer, we've got here plots from 10 different rainfall stations, and there's a moving average there, there's a red dotted line there. And for a lot of these ones, you can see the proportion of rainfall that falls in those 6 month period is actually reduced. So this is actually saying not only is rainfall reducing, and also reducing most markedly in the winter, it's actually becoming more likely to be an increased summer rainfall. The only one that doesn't show this change from more winter to more summer rainfall is Cape Leeuwin on the southwest corner of the region. Now, we do tend to get a bit carried away with rainfall because that's the thing that is easily measured and reported. But I think that what is overlooked is actually the increase in temperature that we've had over this period as well. So this is results. This is the data from the Bureau of Meteorology. So if you go back to 1910 for the southwest corner, you can see that up to about 1975, compared to the average, then the temperatures were below average. Okay, so this is a mean temperature anomaly. This is 0.5 degree, 1 degree. So up to about 1975, there's a lot of blue bars there. But since 75, we've had this higher temperature anomaly. So we've got a double whammy here. We've got a reduction of rainfall, but we've also got an increase in temperature, which is really affecting the effective rainfall dramatically. Also, if it's moving from a winter dominant to a little bit more rainfall in the summer, that means it's less effective as well. Now, the other thing that people have said, though, is that under climate change, we will get increased intensity of rainfall because obviously the atmosphere is hotter, the sea surface temperatures may be higher, we'll get more intense rainfall in future, so we may still get floods because of that. Now, this is a very interesting plot that was produced by Yun Lee and a couple of his colleagues 15 years ago, looking at the daily rainfall for Manjimup. They did it for a number of stations in the southwest. So we've got rainfall millimetres on this vertical axis, and here we've got the return period, in years. So this is the 10-year return period, and the duration of this is for daily. So this is 24 hours. And you can see that before 65 and after 65, they look almost like completely different distributions. So if you looked at the 10-year return period, daily rainfall, now it might be something like 55 millimetres. So 1 year in 10, you'd expect to equal or exceed 55 millimetres rainfall in a day. But before 65, you might have had 75 or 80 millimetres. So what we've got is reduction of intensity of rainfall, at least over 1 day periods. It's a bit harder to say what's happened over shorter periods, like 1 hourly periods. That's much more difficult. But at the moment, this expected increase in the intensity of rainfall as a result of climate change doesn't seem to be apparent in the southwest. Now I'm going to step through those 4 regions we mentioned, and I'll start at the Wheatbelt, as I say, in the east, and we looked at groundwater levels, and we'll look at dryland salinity particularly. Now this photograph here is a classic photograph of dryland salinity that a number of you may have seen before. It's showing a valley with a lot of dead trees. The only things that are living in this valley are the halophytes, or the salt-tolerant vegetation. And this is almost certainly secondary salinity, because you can see the farmer had done a lot of fencing down here and presumably was using this land until it became saline. So those of you who haven't caught up with the causes of dryland salinity, this is a schematic that I've got from a national database. Basically, before clearing, some rainfall was percolating down to a water table, and some of the salt that was coming in that rainfall was being caught up in the regolith, so in the unsaturated zone above the water table. And at least in the eastern states, they had fresh water going into these streams. So you have unsaline land, and you've also got rather fresh streams. After clearing, and you put it under annual crops and pastures, the recharge rates have increased. So you can see these arrows are now thicker. The groundwater levels have risen. More salt gets flushed out into the rivers, and eventually the water tables get high enough that they affect the lower-lying parts of the land, and you get dryland salinity. So this is very, very quick estimate of what's happened. A lot of the Wheatbelt was cleared in the last 100 or so years, 120 years. So this is actually sometimes a very slow process, but the groundwater levels under most of the Wheatbelt is saline, so having rising water tables is not a good thing. Now this is quite a busy little pie graph here, but what it's based on is about 700 bores for which the Department of Primary Industries and Regional Development have been monitoring. And we're looking at what's happened to the trends in groundwater levels in those bores before and after 2000. So there's a lot happening in this pie graph. Basically, we're looking to see whether the salinity risks as exhibited by these bores is actually increasing or decreasing. So if the change in the change in the levels, if you like, the trends are unchanged, then for 17 bores, there was no change in the salinity risk, put it that way. For about another 17%, the salinity risk had increased. That meant that it might have been, if it was rising, it's now rising faster for some reason. So the salinity in that area will have increased in likelihood of becoming greater than it was before 2000. But you can see that most of this graph has actually got a reduced salinity risk after 2000. Now, about 3/4 of the bores were having rising water levels before 2000, but now only about 40% are rising. So when I was working with in dryland salinity, we had a great concern that a very large proportion of the valleys, particularly in the Wheatbelt, were likely to become saline. These trends are now showing that a lot of those rates of increase, or in some cases, the increases now become decrease, that the risks are reducing. We actually did an estimate of how quickly agricultural land was salinising at about 2000, and it came out that about 14,000 hectares per year was going saline. So if we interpret this change in trends, it may well be that in future that 14,000 hectares may be reduced in future. Having said that, though, about 1 million hectares of previously productive agricultural land has now become saline, so it's a massive problem. And as I say, 40% of the bores are still rising, so it's not a problem that's gone away. Now this is showing distributions of where those bores were, and you can see both blue, or hopefully you can see blue and red squares and some white squares. So the white squares are where the trend hasn't changed. The blue squares are where the risk has reduced, and the darker the blue, the greater the reduction in the risk. And the reds are where the salinity risks have increased. Just eyeballing this, you can see that most of those red areas are actually on the south coast. And there's a reason for that. The south coast area was cleared more recently, so it still hasn't reached an equilibrium, so the groundwater levels are still rising, and they might be increasingly rising in some areas. But also, this is an area where the drying, if you like, the rainfall hasn't dropped off as much. So we've actually got a lot of increase, or potentially to have quite significant increases in salinity in some of those southern areas. But the further you go north, this is the areas that we've been looking at, particularly since 2000, which have had a very, very great reduction in rainfall since 2000. You see a lot more blue squares. So that's what's happening to the groundwater. What about the flooding? Certainly when I grew up in the Wheatbelt in the 60s, there were major flooding events that affected a number of the towns in the Avon, and also some of the coastal area, the river in suburbs around Perth. So Guildford and those sort of areas would also get affected by flooding. So by flooding, I mean when there's excess of water trying to go down a river system and it overbanks and goes into the floodplain, and if anyone has got houses or any structures in that floodplain area, they'll be affected by that flooding. And certainly we have this concern that, in fact, as the Wheatbelt valleys were becoming more saline, then the area that in the catchments that were saturated, when the rain started falling, we would actually get increased flooding with time. So this was a projection that was made almost 20 years ago, that salinity would result in increased flooding because we'd have larger and larger areas with high water tables. In fact, this is an estimate was done for the Blackwood River using the flood peaks that occurred in January 1982 after Cyclone Bruno went through. So this line at the bottom here was the recorded flood peak that occurred. So about a bit over 1,000 cumecs occurred in Blackwood in that event. And then projections were made that if the area that was saline in the catchment above that area had doubled, then we'd end up with floods that would be perhaps 2,500 cumecs. And if it trebled, we'd have these sorts of floods. So this was a considerable concern that, in fact, the groundwater levels, by coming to the surface, would result in much greater flood risk. So this was work that was done, let's say, almost 20 years ago now. So we've now, with the benefits of hindsight, being able to look at seeing what happened to flooding since that time. Okay, so we've now got 6 graphs here on the right, and I'll just have to walk you through them. So here we've got the younger gauging station on the Swan Avon system. We've got going back to 1860 and up to the 2000s, the period 2000s. These are the recorded floods that the Department of Water and Environmental Regulation have identified to have occurred on the Swan at Wollonga. So back in the 19th century, you can see there are floods here. Sorry, I should say this is the annual exceedance probability. So let's take this flood here. That had a 1 in 100 year event. So it's 0.01 annual exceedance probability, so this was a 1 in 100 year event. So get this going again. These ones here were about 1 in 30 to 1 in 50 year events, and these ones up here are about a 1 in 10 year event. So there seems to be the largest floods seem to have occurred a long time ago in the Avon. You can see similar sort of trends for the Murray River, Baden-Powell, the Greenock River at Culnew Peak, and maybe, not so strongly, but some of these other rivers as well. Pointing up, maybe at Darrada. So this is the 1982 flood that I mentioned before. Collie, there's no trend at all. And we had Simon Rogers actually came and gave us a seminar last year, and we talked about flooding. And he basically had said that the flood risks that they were worried about a number of decades ago have dramatically reduced. And so they're not quite so worried about flooding in the southwest. So this data is just confirming, I guess, that the flood risk has dramatically reduced, or it seems to have dramatically reduced despite the increased salinisation. Another way of looking at this is just looking at recorded floods in the Avon, also when younger, so back to 1970. But these are actually, sorry, I shouldn't call them floods, they're actually the peak flows that occurred in winter, in the blue, and in summer, in the orange. And you can see that there were some reasonably high winter flows back in the 70s and 80s, and that in later years, that's fallen off dramatically. So those people that are interested in going in the Avon descent, they know about these dry years, they just haven't been able to get very much water to go down the Avon. What's interestingly is that there's normally not very much flow at all in the Avon in summer, but you can see a slight propensity, if you like, for increased flows in the summer. So, if you like, in this in 2017, the summer peak flow was much, much higher than the winter peak flow. Something similar looks like happening on the Arthur River at Mount Brown as well. Almost no flow in the summer, but a couple of summers we've had quite significant flows. So just in conclusion for the Wheatbelt, we've got this feeling that it's actually drying from above as a result of these higher temperatures and reduced rainfalls, but it's still wetting from below because we've still got this rising groundwater, particularly under about 40% of in the bores we're monitoring. So we've also got a fall, or at least a lower rate of rise in groundwater levels to reduce the risk of salinisation in many areas. But as I keep mentioning, at least 40% of the bores are still rising. So it's not that the salt problem has gone away, it's just that the risk has been reduced. And of course, once an area becomes salt affected, it seems to be almost irreversibly damaged. So it's not something that's easily recovered from. The flood risks seem to have reduced, and they all look like, it's still too early, but it looks like it could be that they're more likely to occur in summer than in winter, because the valleys are not getting the prolonged winter rainfall that they used to, where they would wet up and then you'd have a massive, one more rainfall event would result in water runoff. Now, theoretically, higher sea and air temperature should increase the possibility of extreme rainfall events and therefore episodic flooding and salinisation. But to date, and it may be too early yet, but the rainfall intensities don't seem to have increased. Those of you who are involved in estimating the peak flows for culvert design and that know that it's actually harder to do that for a short time periods. So we've looked at the Wheatbelt. We're now going to look at the Darling Range and also the zone of rejuvenated drainage. And again, we're going to look at it in groundwater levels first and then looking at stream salinity. So the image here is a typical Darling Range stream with some jarrah forest in the background. Now, what's happened to groundwater levels in the Darling Range? As a result of concerns about stream salinisation during the bauxite mining, a very extensive network of bores were installed throughout the Darling Range catchments. So we've got a really good record. In fact, John Ruprecht would know better than I, but there's hundreds of monitoring bores up there through the bauxite mining areas. And this is just showing what's happened to 4 of them. So in the Gordon area here, you can see a decrease in groundwater levels between about 1993 to 2008 of about 10 metres. And lesser falls, but quite significant ones have been occurring in these other catchments. So this is quite a common occurrence to see that the groundwater levels have fallen as a result of the reduction in the rainfall, but also the increase in temperature. As a result of this, the stream salinity risks in the eastern Darling Range greatly reduced. As the next slide will show. What is the mechanism for runoff in the Darling Range? Well, there's a couple of cross sections here. When we had much more rainfall, so before 75, there were 3 mechanisms whereby we got runoff. So in red here, you can see these areas which are around the stream valleys, where the soil would have been saturated, so any incoming rainfall would have been saturation excess and runoff immediately into the stream. We also get percolation of water and base flow also contributing to the stream. And the third mechanism is water that infiltrates the soil, hits a clay, comes down the interflow, so this is the green one, and then emerges at the stream. So we've got three different runoff mechanisms occurring when those catchments were wet. When the groundwater levels fall, we've actually reduced to one runoff mechanism. We've now only got the interflow component because the areas around the stream are no longer saturated and we don't get any base flow. So this is quite profound, and it can actually be quite dramatic. You know, it can actually change from one couple of years to the next, you know, when we suddenly get a change in the runoff mechanisms. So we're looking at stream salinities and runoff for an eastern part of the Darling Range here. And here we've got stream salinity increasing up here. So 500 is not really salty, it's actually just brackish. And we've got stream flows here, and we've got three different curves. So this is late 70s and 1980s in the crosses. You can see quite high stream flows and quite high salinities. In the 1990s, both have dropped, and so we've got this one with the squares. Since 2000, we've got very fresh streams, but very little yield as well. So the diamonds there. So it's a reduction in salinity, but it's also a massive reduction in water yield. So now we will look at the western part of the Darling Range, particularly, and the runoff into the dams, which is the one that most people recognise as being the early sign, if you like, of the impact of climate change on the hydrology of southwest WA. So here we have the Serpentine River, and it's the rainfall runoff relationship. So we've got increasing rainfall on the horizontal and annual rainfall runoff in the vertical axis, and three different time periods. So these are the time periods we've been dealing with all along. So the blue are before 74, the orange are 75 to 2000, and green is after 2000. And you can see these profound reductions in yield of these catchments. So if we get 1,000 millimetres of rainfall now in these catchments, we might get 25 millimetres of runoff, whereas before 75, we might have had 80 or 90 millimetres of runoff. So they're just not producing as much water as they used to, and we'll see that in this next graph here, where we can actually see the runoff reductions that have occurred in all the dams, from the Lower Helena and the Mundaring all the way down through to the Wellington Dam. The top ones particularly have had a 60% or more, or 50 to 60% reduction in runoff, but you can see the gradation, and when you get down to the ones in the southwest, it's only 20 to 30%. It's still substantial. Now, a rule of thumb that's been around for a long time is that for about every 1% reduction in rainfall, we get about a 3% reduction in runoff. And also it's an interesting relationship that occurs with recharge as well. So when we've done recharge estimations, we're saying for about 1% reduction in rainfall, somewhere between 1 and 5% reduction in recharge. So it's a similar sort of ratio, if you like, for recharge and for runoff. This is a classic runoff, a streamflow estimate for all of the dams that provide drinking water to the integrated water supply scheme. So this comes from the Water Corporation. And you can see that before 1975, it was over 300 gigalitres per year. So Perth's demand for water at the moment, for the integrated water supply scheme, is just about 300 gigalitres. So just the dams by themselves would have been able to provide water for Perth. There wouldn't have been need for well fields and seawater desalination plants and those sorts of things had the climate not tipped over. Since 75 to 2000, you can see there's almost a halving in the yield. We've had another halving of the yield between about 2000 and 2010, and then a further one. Two of these years, we've got 2010 and 2015, we've actually had almost no runoff occurring. So just to summarise, for the Darling Range areas, as I said, the groundwater levels have reduced dramatically under the forested catchments. While it's reduced stream salinisation risks, it's also reduced the runoff of fresh water into the dams. The processes have changed, so we used to get saturation excess, we've now got more infiltration excess, might be the mechanism whereby we get runoff. However, if we do get intense rainfalls in future, it's possible we will get some runoff and flooding for short periods, but the overall trends are for reductions. So I'll finish with looking at the groundwater levels in the Perth Basin. what's been happening. So this is the fourth of the regions we've been looking at. What the image here shows as a through-flow wetland on the Perth Basin. And some of these lakes are only 1 to 2 metres deep. So a reduction in groundwater levels of only 1 or 2 metres is enough to make these lakes dry out completely. What we were able to do as part of this project was to actually combine the databases from both the Department of Water and Environmental Regulation and the Department of Primary Industries and Regional Development and look at a lot of bores on the Perth Basin. So you might be able to make out there's some orangey triangles here at the top. So there's very few bores monitored in the northern part of the Perth Basin, a lot more around Perth and all the way down, particularly on the Swan Coastal Plain down through Bunbury and Busselton. So what we've got here is the level changes. We were able to find enough bores for which we could get an idea of what the trend was over a 15-year period. So any arrow pointing up with blue was showing significant increases, and there are some there, particularly around Perth where pines might have been removed or an area might have been urbanised or pumping might have reduced. But the predominant colour here is orange and to some degrees red. So some of those areas where you've got orange, which is the predominant colour through a lot of these areas, we've had a fall of up to 1 to 5 metres in that period. And that might not sound like a lot, but as I say, it's enough to remove wetlands. And the red ones, where you've got a 5 metre reduction, is very significant. So the predominant colour is orange and red, as I say. So there's been quite significant impact on the levels. But surprisingly, at least it was surprising to me, was that there's large parts of the Swan Coastal Plain where, even though we've had a drying climate, the levels haven't changed as much as we'd expect. When you zoom in and have a look at the area around Perth and Peel, you see a very confused picture in many ways. The orange and reds here are actually significant changes over a 20-year period between 98 and 2017. But there are also some areas of blue, and these areas of blue are areas where we've actually had a slight rise. So it's a complicated picture when you get closer, but in fact the yellows are also reductions, so that's reductions of 50 centimetres to 90 centimetres. So the predominant area is even reduction in around Perth and Peel. We could go into why each one of those areas is actually reporting that, but we don't have time at the moment. Now what we have done is, this is part of the Southwest Sustainable Yields project, we were able to connect 4 major regional groundwater models to look at what were the trends in groundwater levels under 4 different climate scenarios. So the one on the left here is the wettest of those scenarios, and so they go from wettest to driest, from left to right. This is saying that if we had a continuation of the climate from 1975 to now, what would be the groundwater levels in 2030? You can see that if we had that rainfall that continued, we would still get some areas with blue, which is rising levels, particularly up in the Dandaragan Plateau. But areas where we've got perennial vegetation, particularly in the Blackwood Plateau, we would have falls. But surprisingly, perhaps, large parts of the Perth Swan Coastal Plain would have no change. Then, if the period, this is the 10-year period leading up to about 2009. So it's a drier climate. You can see parts of the tops of the Namgarra Mound falling, these areas where some pines are coming off and urbanisation occurring, maybe some rises. But again, remarkably consistent levels. Once we start going into the future climate scenarios, where the rainfall is projected to fall even further, you start to see the Swan Coastal Plain developing some significant falls in groundwater levels, particularly when you get to the drier extreme climate. Now this modelling was completed about 10 years ago, and it was projecting forward for 20 years. So we've now gone through the end of those 20 years, the projections, and what's happening is it's much closer to this drier future climate than it was to this medium future climate. So what's likely to happen is that there's been a delay in the response of the groundwater levels under the Swan Coastal Plain, but it's actually it's going to catch up with us in future. So this is the last conclusions from the regional studies. So as I say, recharge through the sandy soils, the Perth Basin, we think is reducing by about 3% for every 1% reduction in rainfall. There's a runoff. The levels have fallen particularly under perennial vegetation. because the vegetation is using a greater percentage of the incoming rainfall. As I said, where the water tables are close to the surface, which is on that Swan Coastal Plain, there seems to be a buffering initially against it falling, because what happens is that evapotranspiration losses and drain losses are actually reduced initially, but once those reductions are no longer possible, then we get quite a significant and quite accelerating fall in groundwater levels. Effectively, what happened in the Swan Coastal Plain has been almost completely cleared of vegetation, and urbanisation has really been disguising the impact of climate change on these coastal aquifers. So, just in conclusion, we've been looking at the southwest of Western Australia, but what I've got on this map here is all the areas where we've got Mediterranean climate zones around the world. And if you go online and look at any of these areas and you look at, do a search, you'll find that all of them are experiencing something similar to what we are. They're all experiencing a warming and drying climate and a very significant reduction in water resources. So it goes all the way from Portugal all the way through to Iran, effectively. You've got water shortages through this area. We've all heard about the day zero down in the Western Cape province in South Africa, but other places as well. So we think some of the work that we've done here in Western Australia is actually has relevance to larger areas. So this is my last slide. So in overall conclusion, the climate of the southwest WA has changed significantly since at least the mid-1970s, and maybe since about 65 if you go back to that rainfall intensity work. It's had an effect on runoff and recharge, and it's amplified by about threefold those processes. So runoff and flooding is most produced, and that's the thing that most people picked up when they saw that there was a change in climate. They saw the surface water responding. But in fact, when you look closely, the mechanism is through reductions in groundwater levels in all cases. Obviously, the lower groundwater levels are reducing the risk of salinity in inland areas, but it's also reducing the availability of surface water and groundwater resources in the Darling Range and the Perth Basin. Now, while flood and salinity risks may have abated, they may return if we have a future extreme events, but the overall trend is for a drying and a warming and reduction in water availability in a lot of these areas. And as I say, we think that some of our learnings, because we've done so much monitoring in some cases because of, let's say, the bauxite mining in the hills, it may be that we've picked up things that some other parts of the world haven't realised yet. So thank you very much.
Great, thank you very much, Don. That was fantastic to see all those pieces coming together. I think all of us are sort of well aware of all these individual things going on, but to see such a comprehensive picture is very, very insightful. So we're going to try take some questions from the floor. I'm going to kick off with a question for you, Don, while people work out what they want to ask. So I've often been wondering that now we are looking at desalination, and now that we've been looking at desalination and using wastewater recharge of the coastal plain aquifers, do you see a future where we could be more actively managing groundwater levels to maintain them to around 1970s levels using those artificial water sources?
Great question, Matt. I think we can, but they'll be very localised. They'll be the wastewater resources that we're getting are actually obviously coming from the urbanised areas, so we can actually look at using that to recharge aquifers around the urban wetlands, but it won't be feasible. There's not enough water, basically, to be able to take that water much far away from the urban areas. It sounds like a lot. We're getting over 100 gigalitres of treated wastewater going into the ocean each year. That's 115. Sounds like a lot of water, but when the groundwater levels were falling on the Angara Mound, every year we were losing 45 gigalitres every year, and that was cumulative. So the reduction in recharge as a result of the lower rainfalls far outweighs anything we're producing. So we might be able to do something to save a local wetland, but yeah, it's just beyond our control. A lot of the processes that are in train now are just so far large, we don't have the management possibilities of changing. And
I guess on the surface water side of things, another question that started coming up is around the concept of environmental flows to manage some of these. A concept that's quite popular in the eastern states, for example, the Murray-Darling, but something that we haven't got in widespread use here in Western Australia. Do you foresee a chance where maybe one day we could be maybe augmenting river flows through environmental water allocation, maybe supplied by, say, desalination water?
Yes, in fact, it's actually quite difficult to work out what's happening with the groundwater level, the levels in some of the dams now, because the dams are being used as storages for either groundwater or for seawater desalinated water. So the Water Corporation is pumping water from during the winter when they're using their seawater desalination plants, they're pumping water up into the dams. So sometimes you can go in there and see that the dams have got a reasonable amount of water in them, but it's not runoff from the catchments anymore, it's actually coming up from the coastal plain. And Mundaring Weir, for instance, quite often has groundwater in it because it doesn't have enough water now to supply the Wheatbelt and the goldfields without it being augmented. Now, I think the Water Corporation would be very worried, though, that if they're going to desalinate the sea and put it back up into the hills dams, and then they have to release it as an environmental flow, then it becomes very, very expensive water. So, yeah, it's a policy thing. If they're told to do it, I'm sure they will do it, but I think that it's going to be very difficult to get the environmental flows that were there before the dams were.
Yep. Matt, Jason here. I've got a question for you, if you like.
Hi, Jason. Thank you. Can you go with your question?
Sure. Thanks, Don. Amazing talk, and great to see a synthesis of what you've been tracking over such a long period of time, updated, and particularly like the breakdown via the regions and looking at the different responses in different regions. That was really neat. My question really is, you've looked at the precipitation, so the input to the water balance, I guess, and the other is the evapotranspiration. Have you had a look at potential evaporation or changes in potential evaporation over those same periods of time? Are there any temporal or spatial patterns?
Yes, so I don't know whether everyone heard that question, but the question was, have we looked at potential evaporation rates and how they might have changed? It's an interesting question because people that have looked at things like, and I'm not an expert on this, but you're looking at Class A pan evaporation rates. In some cases, they actually haven't increased as much as you'd expect because of temperatures going up and things like that. Obviously, potential evaporation is more than just temperatures. It's also solar radiation, it's also wind runs and all sorts of things. But the thing is that let's take Perth. Perth's got an average rainfall now of only about 730 millimetres, I think it is. But the potential evaporation rates are about 1.8, 1.9 metres. So we've got over a metre potential evaporation rates are higher than the rainfall. So in a lot of cases, the actual evaporation rates are limited by the availability of water rather than the rates. So the rates might keep going up in some cases, and that'll mean that you'll need to water your lawn more often and things like that, but it might necessarily translate into an increased actual evaporation rate if there isn't water already in the soil, or we've got a wet surface. One of the things that I just didn't have time to talk about, but I think is relevant, is that the winters we used to get had prolonged wet years, wet periods. So we would have days on end, we would have rainfall, and everything wet up, and therefore there was a time for water to soak in. Now we tend to get a lot of short showers that come through, and just what we've had in the last day or two is an example of that. You get everything wet up, so all the vegetation and the roads and the roofs and everything else gets wet up, but then sun comes out, the wind blows, everything dries off again. So the effectiveness of that rainfall is quite significantly reduced. So it's, but if anyone has got any data on what's happening with potential evaporation, I'd be very keen to hear it.
Thank you, Don. Just reading a couple of other questions here now. There's two related to dryland salinity, one from Yuan and one from Warwick. The first question is there any prospect of dryland salinity being reversible? And related is, I'm wondering if the decreased issue with salinity gives us a chance to get more perennials growing.
Okay, it's actually good question. Like, we do know that some areas in the northern Wheatbelt, particularly some of those valleys that had high water tables in the past, have now got water tables that are several metres below the valleys. We don't necessarily see a very quick reversal in that a lot of the salt has been brought to the surface. It's now tied up in the clay subsoils. Quite often when that area went saline, the topsoils were lost, so they were washed away or blown away. So effectively, we've degraded the soil as well as we built the salt up. So even though the salt water table may be down a few metres, it looks as if it's still salt affected. Now, it often occurred to me that I wonder whether there'd be a possibility of someone going in there to see whether they could leach that salt out of that even if it's in the subsoil, to leach it out now if the water tables are down several metres. Richard George, when I've spoken to him about this, says though that all you need is 1 or 2 years of above average rainfall and those water levels will come straight back up to the surface of those valleys again. So while it looks attractive that we could actually go and reclaim some of the areas that previously become saline, it will be very expensive to do that. But what's happening right at the moment is that the satellite remote sensing has been used to remap the areas that are saline, and there could be a possibility that we'll find areas that were mapped as saline just before 2000, which now 20 years later are no longer mapped as saline, and they would be very exciting to see if those areas show up. Now, I've forgotten the second question about Brian's.
Does that give more opportunity for replanting perennials?
Interestingly, you'd think so, but in fact, to establish perennials, you've got to have subsoil moisture. In fact, it's going to get harder and harder for us to establish trees and even sometimes shrubs in some of these areas. I caught up with my brother who farms in the central Wheatbelt just a couple of days ago, and he said that whenever he digs now to look at his water pipes, now there's almost no subsoil moisture. And I actually think that a lot of the crops we're growing now are actually just grown on the topsoil. So it's the wetting fronts are not going more than half a metre deep in some winters particularly, and therefore if you're wanting to establish perennials and you want to have a deep-rooted system that goes down several metres, you really need to have enough water to go in those winters to actually get it down deep enough. Otherwise you'll end up with perennials which will only be rooting the top 50 centimetres, and every time you get a wind event they'll fall over. It's a bit sad.
Yeah, not much good news. All right, we had a hand up by Becky. Becky, would you be willing to ask your question, or I can read out the comment if you prefer? Oh, okay, I think she's not got a mic, so I'm just going to read out the question. As vegetation comes into equilibrium at the stand scale, related to ET and leaf area index, those changes will feed back and affect the groundwater levels. Has this feedback been modelled in any way? Is there an understanding around the new equilibrium level form?
Yeah, good question, Becky. Look, I don't know that anyone's really looking at how the vegetation is responding to the drying climate in much detail. Maybe some of the guys out at Murdoch are doing that, Giles Hardy's group and that. But the thing is that with the climate change, we're not reaching a new equilibrium. It's not like that everyone's got their act together now and there's no more carbon being emitted into the atmosphere. So we're unlikely to reach an equilibrium in hundreds of years at this rate. It's going to take a long, long time. So the vegetation is trying to catch up. One would presume that it's reducing its water use, or it's thinning its, dropping more leaves. Interestingly, and we might hear about this in future, some of the work is showing that there's actually an increased leaf area index in some areas because of carbon fertilisation in certainly some of the more arid areas. So it's a very complicated answer. I'm sorry, I'm not giving you a very clear answer to this. But obviously the vegetation is responding to the higher temperatures and the reduced rainfall and everything else that's going, including the increased carbon dioxide. But how our native vegetation is going to end up adapting to this is still a bit of an open question. But if someone were to come and give a seminar on that, that would be absolutely fascinating. I'd be wanting to come and hear what's likely to happen.
Great, thanks, Don. Another question here on the chat. Don, you compared WA water shortage with other places around the world and concluded it is due to the movement of the climate zone towards the pole. That is amazing. I was wondering, is there any evidence of water surplus because of the movement of the climate zone? So presumably higher latitudes getting more water.
Yes. There is a rule of thumb, and I've never been able to find out who actually said it, but for every 1 degree warming, the climate systems are supposed to be pushed towards the pole by about 180 kilometres. So the idea is to look north of where you are, and if we get another whole 1 degree of warming, then look to the north. So, we may well be getting, Perth might, for instance, be getting something that's up near Lansing or something like that, or even further north in another 50 years. There's several mechanisms, though. It's not just a push from the warming of the Earth. There's actually a bit of a pull factor, and I didn't realise that until a number of years ago when I spoke to some of the guys in CSIRO. And there's an ozone hole effect as well. So the ozone actually has a slight pull factor. So we've got a push factor from the heating of the tropical area and a pull factor from the ozone. And I guess the other aspect of that is what's going to happen to the Lewin current. So we've got a lot of balls in the air. Unfortunately, apart from the ozone hole, all of them look like they're going to make it drier in the southwest. The ozone hole is obviously healing, and so the pull factor from the ozone hole may not be as much in future, but I've asked someone who knows a lot more about it than I do. They seem to think that the push factor from global warming is likely to be significant. Now, as far as whether we're going to be able to get more summer rainfall coming from the north, we did do a study of the climate of the Pilbara area, and you can see a clear signal of an increase in, particularly in the West Kimberley, but also in the northern part of the Pilbara. It's much, much wetter than it was in the last 30 or 40 years. So there is an increasing rainfall, an increasing humidity. So if you go to places like Port Hedland now, they're complaining a lot about humidity. In places like Port Hedland, it's much more becoming tropical. But yeah.
Okay, fantastic. We've got lots of great questions. One more. I think we've got time for one more before we close. There's a question here from Joanna. I'm also keen to know about the effects on perennial vegetation and whether moving to perennial vegetation could provide some kind of buffer to changes in the hydrologic regime, I guess related to the earlier question.
Yeah, so related to it, the thing is that the interception losses are much higher now. So we've done some measurements in Perth, for instance, and what's happening to where the wetting fronts go to in the coastal plain. So this is a very simple system where we've got a sand system. We're actually finding that when you look under a tree canopy now, the wetting fronts are very, very shallow. So the tree canopies are acting like a washing line, if you like. The water comes onto the tree canopy, wets the leaves, and as I mentioned before about the sun coming out and the wind blowing, all that water is lost back to the atmosphere through evaporation. So I like to have trees in urban areas, but it's actually one of the factors of putting them out there is that actually the interception losses will be significantly higher, and we'll get less recharge to our groundwater systems, and we'll actually have lower groundwater levels as a result of the trees. So that's not a good outcome. I'd like to have seen the trees actually having a much more positive output than that, but certainly as far as the water balance goes, they will actually reduce significantly the amount of recharge that's occurring. And I think that's what we can see in places like I said the Blackwood Plateau as well, that the trees are now using up perhaps all of the water that's coming in, whereas before at least 10 or 15% of it was getting past their root zones and getting down into the water tables. The percentage used by the trees and vegetation generally is much, much higher.
Right.
So I'm sorry to be...
there's a lot of information there for us to all take in, and thank you so much for your insights and answering all those questions. Clearly there's a lot of interest, and we're going to keep trying to find some more speakers to help explore some of these issues that you've raised in more detail in subsequent seminars. I know a lot of people came on after I introduced myself, but we will be able to provide a recording of this to you if you wish. So my name is Matt Hipsey. You can contact us through the School of Agricultural and Environment at UWA, and we'd be happy to provide you Don's contact if you would like to talk with him in more detail, or if you'd like a copy of the recording of the presentation. So with that, we do hope that we will have regular seminars going forward again for the next semester, the next few months over 2020. We do hope that we'll be able to have some of you join us in person again as the COVID restrictions start to relax, and we can go for a drink and a chat after the seminars. And we'll keep you updated when that's going to be possible. But in the meantime, we're going to keep trying to get some new speakers. if anyone wants to volunteer someone for a presentation, please do let me know, and we'd be happy to host you and host a webinar to the environmental seminar series. So with that, I'd like to say thank you to Don, and thank you to all of you for your time, and we'll see you next time.